Okay. Welcome to the ibgib channel. I guess it's a channel. It's YouTube, right? Oh, there we go. Let me get that right off from the start. All right. Today we're going to be doing a quick recap of what the ibgib structure is. But the main thing I wanted to get to is right now what I'm coding on is apps, right? So the whole thing with decentralized world is decentralized apps, dApps. And I'm going to show what I've started to do as far as the dApps go for ibgib. And I'm going to show what the actual coding benefit is for the structure, or the architecture. So the whole point of it is that you simplify at some layer the data communicated among nodes. You simplify that, and you reuse the same structure over and over and over in order to gain benefits like you gain with clustering and all those kinds of things, where you are passing or you're taking some amount of data and then you're able to send it to multiple nodes. Eventually, it would be in an ad hoc configuration for which nodes, what level of availability, and that sort of thing. But the main thing, hello, Kitty. The main thing is, I gotta be careful with this one. She's crazy. She's the one in the picture here. She's in my lap. I was gotta be careful with that one. But so the main thing is that there is significant savings in reusing the same structure over what we currently have as different structures. So there's code savings that minimizes surface area. It maximizes code reuse, and it enables more easily things like clustering, availability, multi-nodal configurations, witness algorithms, consensus algorithms, and that sort of thing, and just like code replication or data replication, like Dropbox type stuff. But first, let's go back over what the ibgib thing is. Okay, good girl. So let's look. Let's see if we can just see it here. Let's see if we have it in. Okay, so a quick recap. So this is tsgib. It's hosted on GitLab. I have the other code hosted on GitHub. It's important to be able to diversify. And that's one of the things that this is about portability. But both these things are, of course, on top of Git, which is itself, remember, a DLT, but it doesn't have the metadata and configuration in the DLT. So internally, Git has that Merkle link structure where they have, what do they call it? Their hash database, their hash object database, I think is what they call it. But it's a DAG, and you communicate among nodes through the Git command line. So it doesn't have composability really built into it on top of that. Good girl. Also, remember the Git folder itself is outside of the DAG, outside of their object database. It's sitting there in each folder. So that's also, it's not bootstrapping, right? But so the ibgib, basic ibgib data structure, there's multiple ways to do this. This is similar to, like, say, IPFS, which has, its internal data structure. But this one that I made completely separate from them, ignorant of their existence, instead of hard coding things, I tried to make this as thin as possible. And so I came up with 4 sections of things. One is the data. So the data is for internal data. So this is like the normal, what you would think of as like your, what you would store in a database. So in this, little example of birthday, 111, whatever. So there you have intrinsic data that every time you change it, it's going to mutate this, but it's going to carry it's going to create a new ibgib frame and going to link to the past one using this past relationship. But my point is, with the data, it's replicated every time. And there's ways of optimizing all of this stuff, but at a more composable level higher up, instead of trying to, say, okay, well, how can I fit this and how can I only mutate, now this, what's the one key that changes? So like with Git, which is only works mainly with text, they work with just the diffs. We have a way of doing diffs, but the point is that we're not trying to overly optimize, pre-optimize for this. So data is replicated every new frame. The relations are your links to other nodes. So here's a relation field. It has, in this case, it has a named link. In some jargon, these are called links. They're called edges. Depending on what world you live in, these are called relations. I don't want to get too far into the advanced stuff, but it's not just a DAG. It's not a simple directed acyclic graph because of this past functionality. So a single node in the graph that you're creating, you can think of the substrate, you can think of that as being directed in acyclic, but actually this pass is kind of like a self-reference. So you can have self-references when you start thinking of timelines. So in a sense, it's directed in acyclic, but in another sense, it is not. And that's very, very important to understand. But anyway, so the relations here, with blockchains, you have your block, and then you have a hash pointer to the previous block. Possibly that pointer has some metadata associated with it. In our case, all of our links are not only the hash, depending on use case, which is this gib, but they're also the ib. So that gets me to these other 2 properties. The gib is what most people have as just a hash. So when you send somebody a link to a crypto wallet or whatever, that is just going to be a hash. When you're in Git and you have a commit, they give you the raw hash as the address. And what we have here is the hash, or the checksum, or whatever you want to call it, that is actually the hash of the ib hash of the hash of the concatenated hashes of these, but ib, the data and relations, so the rest of the record, it doesn't have to be that. That's one of the things that differentiates the ibgib style, is that this is like, you know how a lot of times in math or in physics, you'll end up having two equations be very, very similar, but one has, builds up, oh, well, here, this constant is equal to 0. And so that one is a simplification of the other. Well, it's the same kind of thing here. The gib can just be nothing. It doesn't have to have this metadata associated with it. And the schema of the metadata doesn't have to be just a checksum. But here at the beginning, we're making it easier on ourselves that really it ends up being two things. It's either one of these hashes or it's just the string literal gib, which just means there's no metadata associated with it. You don't have guarantees of, the ib and the data and the relations being the same. But so this is the ib itself, and then we'll go back to how these two combine for the address. The ib itself is also another thing that can have its own schema per use case. And this is a little bit less solid, not solid, rigid. And I have not switched over. Jesus, you've been just looking at me. Sweet. All right. One of these days, I'll learn how to use a computer. So I've been going over, if you could tell beyond my huge picture there, GitLab, ibgib, tsgib. I think you could maybe see the address, maybe not. Anyway, these are the four things I've been going over. Data is intrinsic data. Relations are the edges or links, named links. These are actually going to be, you can think of these as primitive ibgib actually also. So, but that's for another time. And then now I'm talking about the ib. Fortunately, no one is watching. Oh, that's terrible to say. Okay, so the ib is just, it's a silly word, sort of a neologism here for the ibgib, is the metadata that we're going to use to pass things around. So this is more like a header with that's involved with each link. Each address in the relations has the ib, and then it uses the caret as the delimiter. Again, that's just an initial standard. It doesn't have to be that. And then here's the gib, which in this case is a obviously ridiculous checksum hash. No, I'm not even sure if that's big enough there. So each of these links contain what metadata we need per use case, whether we want to tell them what, is it SHA-256? We can include that there. Later, we could include the SHA-256 as a flag in the gib itself. It just depends on what we want to have as our metadata schema, which we'll have on chain. So the important thing is this is like a bootstrapping basic schema, and then you can decide, you can resolve later what you're going to negotiate up or down. What is your schema that you're trading, that you're working with. And you can have translators, and there's all sorts of things you can do. The important thing is that you have the metadata that is data that you want to be able to know about without loading the entire record. So if you've already established, say you've already established that you trust a record to the extent that you don't need to verify it internally, then you don't need to load that entire record into memory. if you need to know, like, so for some cases, here I have a couple examples. So if you're having, well, we'll start small. If you just want, name or a title or, sort of like a file name, that's what most people see. That's the metadata that we see. Then you can just have, like we have up here, Bob, and then the hash. Or, more complex, include whatever data you want to have, file name, username, these are examples. And then here, this is for an exchange between nodes where you can actually send, when you're exchanging data between nodes or spaces, as I call them, or as I look at them as, you're sending these dependency graphs, and you can do it transactionally even by having these a known schema that you're transmitting to the others. They can then verify the graph intrinsically, not necessarily with all the authorization rules and stuff on top, but you can verify at the very least that, hey, here each of these checksums work out to be correct. But you can do that per use case. So you can send this ibgib that has this as the ib, and then each one has the checksum, work through the graph, and then you can respond with the same kind of ibgib. So that's the important thing here is nothing's hard-coded in the base graph regarding the schemas, except for the very basic, there is something, and then we're using a delimiter for right now with the caret, which just coincidentally happens to be internal Git. That was a big surprise. So these named relations, each one of these has that metadata and then that. So, you can have multiple relationships, named relationships. Each of them is an array. It's always a many-to-many. And it's as thin as possible. So the most important thing is that we want to be able to pass these graphs among spaces. And we're going to reuse that over and over and over again. So when you think of what is my data that I'm sharing, it's an ibgib. It has this structure. It's like a file. When you have say a DNS record is what we're using as DNS right now. What is a DNS record? It's an ibgib, and it's basically a list of, here's a map of the number or whatever the GUID, whatever version you're using, and then what that resolves to. They're basically just nicknames. But so you can transmit all of that data using the same mechanism, minimizing your need for maintaining a larger code body. And so one of the other examples that we're going to look at now is what I'm working with the apps. So right now, that's definitely what we got. So this starts up the in-memory Angular server, npm start. FF0, so this starts up using WebEx. It actually starts up a profile with a Firefox instance on a different profile. and then includes the ibgib app as a web extension, but that's not what we're going to use. Because we can also just go to that Angular server now. Is that going to be? And then for the video, so I can make this a little bigger. We'll see how that goes. So there, that creates a local space. It's now creating some of the initial data. All right, so we can go to our home tag. This is what I'm working on right now. We don't have an app explicitly created. We'll also show the robots because this all has to do with what I'm talking about with code reuse and the ability to just send projections to have them mobile. So if you have an IoT device on the edge, however you want to think about it, when you have an AI model that you want to send somewhere, when you have data that you want to replicate, all of these things are simplified, which reduces complexity, reduces attack area, the surface area. It just streamlines things. So we'll see it with like this home. Right now, home is an ibgib. Okay, this is our tag. This is kind of like a bookmark. If you think of a browser browsing web 1 and web 2, a tag would be like a bookmark for web 3, where you can be on whatever ibgib and then you can tag it with something which is going to add a link. Here, we'll just, since I'm still going over basics. So now, before we were in the tag, home tag context, now we're inside of that comment. We've just gone to this address, which has that ib. It has the gib as the metadata. And this thing itself, the comment, is an ibgib. And it has intrinsic data. Some of it is metadata, like this n is 1, timestamp, UUID. And then the data for the text itself is in here, and it also has a metadata timestamp. Of course, using the local time. So that's a fun part of there. So this thing, we can tag it. We could create a new tag, create our favorites, and we can tag it with the favorite. Now we go over to the favorite tag. It's going to have that on here. That mutated the favorite tag. It puts a relation on the favorite tag of targets to that comment. And so now we just increased our Merkle DAG, right? So these Merkle links, these hash cryptographic links. And so you can see we're growing a timeline. In this case, it's the tags timeline, the favorite tags timeline, as well as the index. So this tag itself is indexed in the local space. So we've actually mutated that local spaces tag also. There's also a latest, but that's ephemeral. Don't want to get too lost in the weeds here. The main thing is that we can send just this comment. We could send that to another space or another node. We can, and replicate. When I say send, that's also replicating. That's also merging timelines. So if you think of Git, where you apply changes when you do a merge, when you do a branch to a different branch, make those changes, and then you get merged back into a different branch, you're applying those diffs, those the deltas between commits, those hash commits. And so that's exactly how this works, only it doesn't work at the text level, it works at the transform level. So we're able to replicate this comment, either just a straight replication or a merge into a different timeline, representative timeline. I mean, that's how syncing works. But anyway, we can also do that same thing with the favorite tag itself. And we can do that with, we'll just do a quick robot. So here's the simple robot that I have in place now. We just instantiated that sort of class of robots. So this robot right here, like we can go over here inside of this comment. I double click that because of there's just a little quirk with navigation, and the browser navigation history is fun to deal with. But so we can go inside of this comment. So instead of tagging it, we can also sort of tag it by putting it in this robot's sort of field of vision. So we just told Randy, hey, Randy, look at what context we're in right now. And then now if we go to Randy, because remember, this robot is an ibgib, like its memory is an ibgib. If we look at Randy, you'll see it in the background there, the list. So there's the comment. If we look at the raw data for Randy, we have to use this little thingy now because I'm actually working on the app, that the view into the data where we could see it in the main prototype here. But if we look at Randy, so now his in is 2, he's mutated a couple times. Version 1, that's kind of like event sourcing where you say what version of the thing is. In this case, the robots. It's got some basic data. You know, here's the class, class name. No, you know, can't see that at all, and that doesn't change it. You know what? Here. Because we can see this. And then go ahead and toggle the screencast. Okay, so all right, so this is the code. This is the data for the robot instance that we just created. And here, inside of its intrinsic data, the internal data that's going to be changed between each frame when we do a mutation, sort of like when you mutate an array and create a new array. So these ibgibs, every time you create a new one, it has this DNA right here, right? So that's how our transforms are done. Each of those DNA transforms are ibgibs, so you can send the metadata along with the data. And in this case, we'd also be able to replicate the robot and what you can think of as the chatbot. By the way, it's double B's because of in honor of Robbie the robot. If you've ever read the robot stories from Isaac Asimov. But so a more biological view of robots there. Sort of like this is more biological view of programming, of coding, even using the word DNA for our relationship to the transforms. And so you end up with the same kind of thing with a genotype and a phenotype. But anyway, we also have some other metadata here for the robot. We have some metadata for internals for this particular app. Right. So, Randy, when we go to a different space, like say I started up a different computer, I can now replicate this timeline and either move it, meaning like you would seal it on this local space and you would send it to another space, sort of John Carter style, where you copy the brain or whatever that brain space and you project it to another projection. And so now we have this one would be sort of dormant. And on that other space, that would be the active space, we would have this robot, our robot. So you can think of this same thing being used for models. So when you train an AI model, like how do you move that AI model from space to space? That's going to be a problem that people are going to solve with a lot of code. It's going to be very complex, very easy, and very brittle to break, and very hard to maintain. Whereas this, again, because we're dealing with timelines and timeline projections as our primitive, we're going to be able to send, our local robot going to be able to teleport from IoT robots out in the field to here's our, servers over here in this other place. This is a simpler way of enabling projections among spaces and how to deal with the dynamics of those spaces. Very similar to how you are used to, if you're a coder, of sending, of cloning a repo from the almighty GitHub. When you clone that repo, you're creating a different timeline. And now you have these, even though it's the same branch, now you have a remote timeline, or your origin timeline and your remote timeline, your local timeline, that looks at the origin as a remote, and vice versa. So that's their local space, and then the other one is the sort of the outer space. But so those are timelines. So this is very much about how, the same kind of primitives of those timelines, where we do a fork, where we mutate. Both of these are mutations on a single timeline, but mutate is specifically to mutate the data intrinsically, and a relate is changing, either adding or subtracting or both inside of here. That's an implementation detail that, for version 1, it doesn't have to be that. The main thing is that we are capturing the transform as an ibgib. We are capturing each of the transforms, and then we are capturing what order we've applied them. So very much CRDT now has been a recent big craze. This is very much like order independent CRDTs, where you can say, okay, well, they've applied these same DNA. It's going to be very, very similar. It's not going to be exactly the same because different DNA can have local time dependent things. And we can code for that later if you want to have a closer attempt at pure functions where that's not really, really possible. But It's a philosophy or maybe a religious war there. But the main thing is that we're dealing with timelines and how to send timelines to minimize our code. So this same thing, when we go to our comment data and we want to send this comment, so when we synchronize to the space, this little button right here will try to synchronize to an outer space. I have to create a secret. It's like a password right now. Okay, we'll just go through it. So let's see, right? And then here, this hint, this is for metadata. Just for me personally, you don't want to have some password manager control your existence by putting your password inside of it, your entire password. So you have one of the things that I love talking about is the ability to learn things with ibgib. That's my driving use case is for distributed learning and has been for way too long. So in this case, I'm going to do a terrible thing and say, that's too explicit of a hint, but obviously this is contrived. But so we're going to create that secret, which is creating it in the form of an ibgib. Now we're going to create an encryption setting. So for me, blah, 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 whatever. Right now, all I have is encryptgib. I have a terrible video where I didn't have my sound on. Just looking back at the mic, see the mic's doing something. So I went through the encryptgib library. If you want sound on that, if you're watching this, I'd love to put sound on it, but I'm not going to waste time on it until somebody wants it. But so this whole ibgib this thing's going to create is going to create an encryption setting, like a parameterized setting for whatever the encryption method is. I've only done this one. So here, you got your pseudo, but less than pseudo random thingy here. Here's your parameters. I'm just going to do twos. Use the SHA-256. In this one, you actually can use the SHA-512. It's still not super secure. Oh, name's probably too long. Whatever. And then here, because you are in control of your data, these are like adapters. So this would be an ibgib that we have to encrypt. So that encryption is not for our data itself. It's for this information here, which is going to be sitting alongside, and then we're going alongside of our data in the same bucket in our local space. So it's going to encrypt this data. So when you go to send it off, and I'm not going to go through this right now, but so this would set up an outer space that we would use for synchronization, right? So when we go to synchronize, send this off to that AWS DynamoDB outer space, what this is actually going to do, you can have multiple people as long as they're looking at the same outer space, the same, right now it's cloud. If they're looking in the same buckets, then they're going to have access to this address. This ibgib comment here is a comment, blah, blah, blah. They're going to have this ibgib, and then the way it does the merging is more like a git merge. So It's a new keyboard. So there's different ways that we reconcile differences between nodes. And in this case, it is the one in AWS, is that more recent than your local one? Can we do a fast forward, sort of like Git? Can we do a fast forward merge, or what? Can we merge using that DNA, which is, like I said, like the CRDTs, where order does not, right now, in this case, order doesn't matter. So when we are synchronizing to the outer space, we're not just copying the local space, sort of like a file. We also have the ability to merge dynamically and sort of git merge, as opposed to just a git, a file copy into the space. And that's very, very important. So all of this, what I'm saying is that this robot that we have here, when we want to go have our chatbot or whatever have a local presence, uh, a logical, physical presence somewhere, uh, then we're able to send that robot. Same thing with our data. So when we want to send this comment somewhere, it's the same mechanism. It's the same mechanism for the timeline synchronization. And same thing with the tag. When we want to, duplicate, say we want to back up our tags. And so on some other space, I want to have this home tag. Then I would go to the home here, had it synchronized to the outer space, the cloud space. And then at the other local space, I would then import it. Importing's down here. So there are no apps right now. So this is actually defaulting to a chat view of our information. So this is our context up here. This home tag is our context. This comment is inside that context. And right now, our default chat view is displaying, it's opinionated on what it's showing. A chat is just, it's a linear view of certain events. So here is another comment, 1121. Right, we can add a picture, or multiple pictures. Right. So this is a view of this home tag. We're doing all of this inside of our home tag. We wouldn't do it normally on the tag itself like this, but so we're viewing this home tag as a linear view, just like you would have as a chat. That's all that means. So it's adding those pictures. But we don't have any apps created yet. So that's what I'm actually working on right now. Instead of hard coding it as just this chat view, in previous prototypes, I had a view bar where you would view this home tag in different, very much like in Windows, you can view as thumbnails. I'm not sure if you can do it. I'm not a great Mac person. I've just only recently started using it. But let's see. Oops. Well, I don't want to go through that there, but so when you look at the Finder um, in Mac, it has a little button that you can click. It says as icons, as list, as columns, as gallery. Those are how you're viewing the same data. So you're inside that folder, but you're viewing the data differently depending on how you want to view it. And so with decentralized applications, where the data is able to move around more easily instead of being, entrenched in just one silo, you're able to move your data and, say, okay, well, this is where the data is actually located right now. Here's the live data. Very much like in Git, how you can say what is the head, what is your main branch. Um, so we will create an app. Looks like I have debugger statements here. So very much like we created the robots, we'll go ahead and create a chat app. So it's just, for right now, it's just a couple basics of it, but you can think of apps in general. Usually you have like a profile, like your profile contains this information, and maybe that's how we'll do it in the future. But for right now, um, just have a couple things that are directly on the app. Maybe in the future we'll have profiles that we're attaching to this app. But this is more like, instead of having a single app, uh, one of the things you start thinking of in terms when you're dealing with just timelines is you have the thing, and then you can actually fork that timeline, which is very much like instantiation, or having kids that have your DNA. Um, so in this case, we're creating an app which has this hard code. Right now, it's hard coded and out of band. So once we have version control within ibgib itself, you'll be able to point to the actual source code. But so this chatgib code is hard coded right now in our source code. So that's out of band for us, but in a different DAG. So here's the data for the chat app, right? So this is the data. Why that's so big. So here's the data for that app. Right. And then here's the rendering for when we have a chat app. So here's the view part of it. Right. So all of this is out of band of how these things work, or off chain, I should say. But again, we're going to get to the point where these are more easily interchanged. So instead of living in a different GitHub DAG, all this will be just in the same DAG, and then you'll be able to go all the way from the source code and then sort of reify or compile, um, very much like going from the genetic code to compiling to us, the phenotype, the instantiations of this. So, but the important thing is that for right now, at least, we have, if not the code, we have the parameterization of these apps on chain. And so now, just like with the robots, another one, just like with the robot Randy, who is an ibgib, or this comment, or this tag, or anything else, we reuse the replication capabilities, the cryptographic replication capabilities, and we're able to transfer your application parameters or configuration just as easily. And so now what does that do? That reduces our code that we have to create and maintain, because we're no longer writing a different code for some pipeline to move the stuff. Moving a robot doesn't take anything special that's different from moving the chat, or moving your data, or moving your metadata, or copying your metadata, or replicating your metadata or your data. So hopefully that gives a good idea of, we're right at an hour. That gives a good idea of something that's difficult to describe to people, this abstract, savings of, what does this actually gain? What's the point of this? And so this is only one aspect of one of the things that gets streamlined with using this data. And it doesn't have to take over other databases, because, and also like with other cryptographic approaches, like smart contracts, you don't have to, we want to get to the point where you do not have to learn a new bespoke language in order to do this. This is at the protocol level, and you should have, just like you have the ability to point to versions or releases or tags in GitHub of a compiled version, you should be able to do the same thing with your quote unquote smart contracts. But the point is that that dynamic code is probably going to be simplified in whatever language you have, or more standardized. And here, that's what we're doing. It's not like it's trapping you into one ecosystem. You should be able to use whatever language you want, just like you already use now. It's just, instead of using Git, or maybe on top of using Git, because it's actually can subsume it, on top of that, you just have this one thin layer of, okay, now I have the ability to include data and metadata in my projections. And now I'm dealing with timelines that I was already used to dealing with Git. But now we're working not just at the text level, we're working at a per use case semantic level, for what we need to transfer from point, node A to node B, or space A to space B, depending on how you want to look at that. So I think that's probably a good enough time to end on. Thanks for watching. If you are watching, let me know. Oh. And yeah, I'll see you next time. Thank you.